Hello folks and welcome back to my basement. I'm here today to finish the lecture that I gave in class on Thursday, but that did not record because my recorder shut down for a second time. I'm hopeful to get all my technical problems solved over the weekend, but who knows? We will find out. Fortunately, I only lost about 20 minutes or so we will go through this and try to make it work. So I'm starting a few slides back to give the context. We were reviewing the concept of division of variance in empty models, the idea that in longitudinal data, our naive starting point is not just giving each person the same fixed intercept, but incorporating the information about their own person mean by using a random intercept. So in this diagram, we have three people, blue, yellow, and purple, and U0I is the individual value for each person's random intercept that conveys how far off their person mean is from the mean of the person means as given by the fixed intercept in this figure for the red line. So if you are someone whose mean is above everyone else's, your U will be positive. If you're below everyone else, your U will be negative, as in the purple person here. And the collection of the U0Is, the variance across people in the random intercepts, is notated as this tau squared sub U sub 0. So I made the point of this that U0I is a value for a specific person. The variance across those values is given by this, which is the actual model parameter. We don't need or want the individual U values because they are shrunken. That means they'll be pushed towards the fixed intercept to the extent that they would be more extreme and also to the extent that someone has fewer occasions and thus lesser reliability. So at level 2, the collection of U's represents between person differences, inter-individual differences. At level 1, the E's that remain, so once we use the U to get down to our person mean, E is how far off each occasion still is from the person mean that's predicted. So ETI is a value for a residual at time t for individual I. It has variance across occasions and persons that we assume is constant, denoted as sigma squared sub E. That is an assumption, but it is a choice, and you can extend the model to allow different variances as a function of predictors, occasions, and what have you. But point of the story, the idea of the E here and the variance across the E's is within person longitudinal variance representing intra-individual differences to be predicted by time-varying information. So in terms of equations, we would compare and contrast a single-level model against a two-level model where the E from the single-level model has effectively been split into two components. Between person variance that is represented by U0I in this equation, so this is a value for this person, but it's representing the idea that we have between person variance in the random intercepts. Likewise, E is the level 1 residual. E is a value here, but it's representing the idea that we have within person variance over time as level 1 residual variance. If you were to then take what this model says the variance of y should be across time, it would form this pattern in our V matrix. So V is the composite total marginal put back together again version of what the model predicts the variance and covariance to be for each occasion. As shown on the diagonal, the variance at each occasion is part because of between person differences at level 2 in the intercepts, part because of within person differences in the residuals at level 1, and this model says the variance is supposed to be constant over time with constant covariance regardless of which pair of occasions it is, because the only reason there is covariance is because of these person mean differences as implemented by this random intercept variance. So how this gets built is by taking the G matrix, so this holds the level 2 random intercept variance for now. It more generally will hold random effect variances and covariances, so G is level 2. It's combining it with the level 1 R matrix, which per person has the number of rows and columns that that person has occasions. This is a diagonal or independent R matrix structure that says the E's are uncorrelated because the only reason they were correlated is over here in G instead. And then there's one more letter that shows up in the mix, which is Z, which is a matrix that contains the values for the variables to be given random effects. In a random intercept only model such as this is just a column of ones where there'd be as many ones for each person as they have occasions. So the most important thing the empty model provides us is an indication as to how much of the variation in an outcome is actually cross-sectional and versus longitudinal. So intra-class correlation, and yes, there are many kinds. This is also known in the literature as ICC1, particularly in the context of cluster data. This tells us how much of the total variability is between persons due to person mean differences in particular. It also tells us the expected correlation of occasions from the same person. And said differently, the ICC is an effect size for how much of the data is due to constant person dependency. So it ranges from 0 to 1, where 0 means no between, 1 would mean all between. So in class I had said if the ICC is 0.3, how much of the outcome is longitudinal within? That would be 0.7. So the ICC directly gives you the proportion that is between. Then we talked about fixed and random slopes for time. So this is the idea that in studies in which time is the point, so occasions are far enough apart so that you can see change happen, there's two types of questions that we would want to answer. Is there an effect of time on average? So if I plotted the average trajectory given by the means, would it be something other than flat? If so, then we need fixed effects related to time to be able to capture those trajectories. And then, does the effect of time vary across people? Do people need their own versions of the trajectories, either flatter or steeper, higher or lower, that kind of thing? If so, then you need a random effect of time. So in this context, fixed is the part that everybody gets the same. Random means everybody gets their own. And I have examples using linear time, but there's many other kinds of change possible, as we saw last semester and as you might see in Chapter 6. So in these diagrams here, the intercept is random in every figure. The question is, what do we have with respect to the time slopes? So the empty model predicts what it looks like here in panel A, where the x-axis is time, the y-axis is the outcome. The heavy black line is the mean for the sample. It'll be drawn through the dots, and the thinner black lines would be for hypothetical individuals. And this plot shows no fixed effect of time because on average the trajectory is flat, and no random effect of time because there is no change and no changes the same. So everyone behaving in the same way is the key idea here for the absence of a random effect. If we were allowed to make a fixed effect, then we are saying, yes, there's some kind of change on average, but everybody changes the same so that we don't need a random slope of time in addition. So these two panels are the only situations in which the repeated measures approach, univariate approach to repeated measures rather, as implemented in ordinarily squares in most cases, that these are the only pictures that would be consistent with that, because these both show constant variance over time and they imply constant covariance as well. More interesting is the case where we have no fixed effect of time, but we do have a random effect. That's because on average, it looks like there's no change. However, when you dig into the individual level, that's because some people are going up and some people are going down, which are canceling each other out. And so now we have heterogeneity of variance as a function of time. People are less spread out in this picture at the beginning than they are at the end, and that also introduces heterogeneity of covariance over time. And then you can have some of both as well. So you can have an average trajectory that is not flat, coupled with individual differences in the extent of change in that trajectory. So switching to two-level notation then, this is the panel A, empty means random intercept model. We have y at level 1 per time t individual I is a function of an individual specific intercept. So this is neither red nor blue because beta 0I is not a parameter. It is, as we called it last semester, a placeholder. I also like to use the word backpack because beta 0I is a container that says how each person is going to get their own intercept out of model parameters. So we have the fixed intercept, which becomes the mean of the person means. Here is the random intercept for person I. This is not the parameter though, this is a value. The idea is represented here that we have a variance across people as what we're actually estimating and caring about. We don't need the U0s as individual values, and it's not useful to have them in many cases because they're going to be shrunken. Then after each person gets their own intercept, we feed that back into the level 1 model, and then E is the level 1 residual at that occasion for that person, and it has a variance too that we assume by default to be constant. So without the beta 0i placeholder, we can see more readily through composite form what is going into the model. And I said in class, as a way to connect to what is coming, you can also think of beta 0i as a latent variable, such as a factor score in CFA or theta in IRT. It's the same idea. We don't typically write it by separating its mean and variance parts, but that is how it's written in multi-level land. We will see connections to how to express this using SEM notation in software as well, but beta 0 is going to become a latent variable with a circle eventually. If we add a slope for time that is fixed only, so we're talking about panel B in the previous picture, fixed linear time random intercept, that means we're adding a second beta placeholder. Beta 1i is how each person gets their own linear slope for time, in which time should have been centered so that time 0 is somewhere within the span of the data. The first occasion is often a good choice for that. And so beta 1i comes down here in the level 2 model, and this so far only has a fixed slope, so everybody changes the same as indicated in the composite notation as well. So what we're saying with respect to variance and covariance then, a fixed slope model is still consistent with a compound symmetry V matrix. It's saying that the variance stays the same over time because the trajectories are indeed parallel. If we were to add a random slope, and in class I said let's play Where's Waldo with dense slides and notation, and folks were able to narrow in on the new contribution right here, U1i has been added to the prediction of beta 1i. U1i is a random time slope, so it is how far off of gamma 1o, which is the fixed slope, now the average slope, so it's the average time slope across your sample of people. U1i is a deviation from that. So now everybody gets to have a different rate of linear change by making an addition to the fixed slope. So if the fixed slope is positive and I grow faster, my U1 would be positive. If the fixed slope is positive but I increase at a slower rate, then my U1 would be negative, still culminating in a positive slope overall, just less positive than other folks on average. And so when adding this new variance of the U1i's is the new term right here, we're also adding a covariance with the random intercept because the random effects from the same person should be correlated. So breaking this down into composite notation then, the black line is the mean for the sample, the blue line is for a particular individual. The fixed intercept then would be the expected outcome as determined by the line at time 0, which is right here in the plot. So it's not the exact mean at time 0, it's the one that's predicted by the line. U0i then is how far off that person's intercept is as determined by their line. So it ends where the line is as -4, which means this person has an expected intercept of 6, a little bit below, or excuse me, above where they actually were at that occasion. Gamma 1o is the fixed slope. So to the best of my PowerPoint drawing abilities, this is rise over run, change in y over change in x. The outcome increases by 6 per unit time on average. U1i would give you the random slope addition for that person. So their random slope would be in this picture a +2 because their rate of change is 8 instead of 6. And then E is the deviation that remains from the line at each occasion, which is possible to observe so long as you have 3 or more occasions. So that would be the minimum to fit this model for it to be identified, meaning to have enough information to be able to differentiate what is individual differences in change from what is level 1 measurement error. When you only have 2 occasions, you can't split them apart. You either say with just 2 occasions, because each person, if they get their own line, it's going to fit perfectly, the two points they have. You would either have to say that you have individual differences in change that are perfectly measured, or that everybody changes the same, but there's some residual variability around that. It's 6 of one, half dozen of the other. So random linear time models then imply 2 different kinds of person dependency, 2 different reasons for the correlation of occasions from the same person. The random intercept part introduces a constant dependency. The random time slope part introduces a non-constant person dependency. So now we would have a G matrix that has 2 by 2, intercept, slope, covariance as well, Our R matrix is still diagonal or independent, testable assumption as well, but we're saying that the only reason that the outcomes were correlated is over here in G, such that the E's are independent, just like they are in standard regression. So I believe this is where we ended up with, because I promised not a lot of math at the end of class on Thursday, and I will hold to that promise. So this is a picture then would be consistent with this random linear slope model. People are changing at different rates. That introduces heterogeneity of variance as a function of time. So there will be some point where there's a minimum variance across persons, and then the variability will increase as you move farther and farther away from that minimum. And in fact, it works out that the pattern of heterogeneity is quadratic across time. It creates a parabola, a U shape in this case, because within the variance function that is created by this, as shown on the next slide, time squared shows up in there. Likewise, if I had a random quadratic model, time to the fourth shows up in there, creating what I call a quartic pattern of heterogeneity of variance over time. So this will be an issue that shows up not just for time, but for any time-varying predictor that is given a random slope in these models. So compound symmetry will not hold, constant variance will not hold if people change differently. And that's where we're going to stop for today. Thanks for being here. And as the kids say, smash that like button, grab the merch, and hit subscribe. Thank you. See you on the other side.